So hello, this video is about a Jupyter Notebook example on Monte-Carlo policy gradient or reinforce. Just let me switch off and move the screen. In this video, as always, I will not distract you with my video, but maybe just go on. So if you go into the download folder, you can actually find Monte-Carlo policy gradient Jupyter Notebook. Just make it full screen. What you see is, and you will find something like this. Let's really do it step by step to actually introduce the notebook a little bit to you and also enable you to actually work with it. So at this point, I would really like to thank Tim and the other authors of these two sources were actually pulled most of the stuff to actually compile this Jupyter Notebook. So what do we do in the beginning? So in the beginning we do all the imports. We will need a gym, we will need NumPy, some plotting. This is also for plotting here. And we will make use of Torch as a neural network library to actually do the optimization. Yeah, so just get things started. Let's use let's just initialize OpenAI Gym. We will use carpol v0, and we will also seed the environment, which basically means that upon a reset, we will actually always get the same results. And we will also use this in Torch. Yeah, so actually, let me just restart and clear. Yeah, so these tools, we can just run them, and then the imports are done. If we do policy optimization or Monte-Carlo policy gradient, what we just need is a policy network. And a policy network, these are just hyperparameters, you can just remember them. And the first, we just need to define our policy network. If you use PyTorch, you will maybe already had made the experience that you can define a network and also like tweak everything inside it with very little code actually. So this is our policy network. Our policy network just inherits from a neural network module, and it takes the environment's observation space as input. This is defining actually the number of input neurons. It's just what we get from our environment, and the output neurons are just how much actions we can actually take. So many actions we need. We need one hidden layer with 138 neurons, and this is how we actually what we actually need. We actually initialize a neural network layer that's taking in the state space, the size of the state space, and has number of hidden units. We introduce a dropout layer to actually during training do the dropout, and we have a second layer that actually produces the output. We maintain a history of our rewards, and in the beginning we reset, and this is how we actually connect our network. So the output is just the softmax over what's coming out of the second layer, and the second layer is a ReLU over a dropout version of the first layer. So this is actually our network, and defining the forward pass. Everything else is done implicitly by PyTorch. So if we want to run our policy, so think about we have a network running. Given that network, actually, how can we sample an action? And what we need to do to sample an action, we just want from a state having the output of a network, which is just giving the state. So actually, what we just need to do is we need to create a tensor from our state representation from OpenAI Gym. This is like a boilerplate code we need to do. And what we then get out of our policy is action probabilities. This is actually what we get. So running the policy network with our state just gives action probabilities. And what we then do is, this is actually what we saw in the latest, which we will see in the next slides, that we use these action probabilities to create a distribution over it and to sample over it. This is what we do here. So we could also take, this is a categorical distribution. We take the action outputs and we initialize it and sample from the distribution to actually get a discrete action that we can take. Yeah, so and then what we do is, before we actually return the action, we just need to maintain, or just for the policy estimation of the policy gradient, what we need is we need the log product of the action given the state. This is what we maintain here in memory, and then we return the action. Yeah, so this is the reward. Imagine that you run your policy, and now we want to update a policy. So we actually maintained all the probabilities throughout an episode. And what we do in the update policy function, at first we need to calculate the rewards to go. This is just starting from the back and calculating the R value, which is basically the current reward plus the gamma of the next return. Gives us the reward to go, and we insert this, and so we start in the back of the episode and maintain a list, and always insert the next one in the beginning, and in the end we have a list that's as large as our episode -1, with all the rewards to go. So we scale them that they actually have common value range. And then we calculate a loss on it. So actually multiplying it with -1, which actually gives us something to optimize towards. And we want to optimize, and this basically then says that we want to optimize. This basically gives us a gradient estimate, or an estimate of these G value. And in order to actually perform a backpropagation step to increase the action along this sequence, what we do is we do the zero, the gradients, backpropagate the loss, and perform one step through our optimizer. Yeah, and what we do is we maintain history of the rewards, and we add it to their history. And then we reset our policy, and we can start over again. Policy reset just implicitly removes the episode rewards in order to let a new episode run. Yeah. So then we do the training. In order to train, it's also very simple. So we maintain all the episode rewards, and for all of the episodes we plan to run, actually, this is what you also saw in all the OpenAI gym examples. In the beginning, you reset the state to get an initial observation, and then from time t until some maximum point. You just keep on predicting an action, take this action, receive the next step, append this to the policy, and do this until either the time is over or the episode ends. And then you keep track of the reward you actually got. And this is just boilerplate code to keep things, to visualizing things, and to see if you're done or not, also if you solved the environment or not. And And then in the final step here, we would call the update policy. Basically, we update the policy whenever we actually obtained a new episode. Okay? So for any of those episodes, we want to increase the probabilities defined by the actual return we got through this episode. Yeah, and in order to run the model, we just need to initialize our policy network. We need some optimizer. In this case, we just use the Atom optimizer, and we take our parameters. I think the learning rate was 1e-2, and we want to train for 500 episodes. And now I forgot to actually run all this code. Let me just do this. So run. This should be also only definition, so it should get quickly. Everything defining, and then now the real big thing starts. I do not think I need to pause the video, but what you see is we run episodes. It really gets quickly, and you see the average sum of the rewards we obtain. And what you will see is that I think now it's Carpol v0. In Carpol v0, we solve it after 298 episodes with an average reward of 195.81. Yes, so the results are as expected. I could predict it because the seed returns the same random numbers, and so we can have a deterministic behavior of our training. And yeah, so what you see here is that Carpol is solved after not nearly 300 episodes, and we can also plot the results. So this is actually the episode length over the episodes we are in training. So this is after 300 episodes where we ended training. Our episode length was 200, which is basically also the reward in this case, because we get a reward for every time step. Yeah, so here you see the average reward plus the standard deviation. Yeah, so in Carpal V0, if you look into it, the episode is cut off after 200 time steps, so you cannot do, and you get a -1 reward, +1 reward for every time step that you actually into the episode. So that's actually defining the maximum. But the environment tells you that if you have a reward of 195, you can actually consider it to be solved. There is a Carpal V1 environment, which is basically the same dynamics but different thresholds. So an episode has a maximum length of 500 and only then terminates. And the reward threshold of solving is 475. If we change this around, so we can also change V1. We only need to do this one. And then we can run it again. And I think it should also work quite well. But in this case, as we need a policy that maintains the performance for a longer time, we will also need more samples to actually cope with all the states and all these situations. And now let's see. So in previous calls, so actually you now see that the average sum of rewards also is even better in here. This is due to a different random seed in the environment. But what you see, if you want to actually solve Carpal V1, we just need around 600 episodes or 473 with an average function of this one. Yeah, just let this thing running too. I think we can wait without stopping the video. Just taking 73 episodes more. So it's just running on my MacBook. No big deal. So it's just an Intel Core i7. If you have something similar from the last 5 years, you can also run it on your laptop. And here you see that Carpal V1 is also solved after quite some iterations, but still only working on my laptop. You can also visualize it here. There you see also some drops in it, but you are familiar with them right now. Yeah. Feel free to actually use this as a vanilla variant to actually maybe also plug in all the results and also what you learned from the actor critic examples. So if you actually want to introduce a baseline, this could be really easily done. Really take maybe some time to dig through the code and do it. What you still would need to do is you would need to add a second neural network in here, which is not only your policy network, but your value function network. You can just add another one here and initialize it. And here, and where you calculate actually your R, which is what you then use for the optimization. You can just play around in here and add the baseline, basically. And if you also do this one, you can also introduce the actor critic variant of it. All of this you would actually do here, because this is actually the only thing that changes throughout all the different variants of actor critic and policy gradient methods. Yeah, so please download the source code and make it running. I think everything is working out well. If you have any questions, just approach us and we can help you.